radiation limits are in some particular system.
Different usage.
And they're used to dealing with one particular kind of radiation, like say gammas, where the numerical value of the Sievert's higher. Well, then they somehow think that they're dealing with something else, but the numerical values are always the same.
Okay, Dr. Dodds is off getting examined this afternoon, so I'm filling in. And it's my honor to introduce Dr. John Frazier. He's a president of Oxford Associates, but I might mention that Dr. Dodd's wife used to work for Oxford Associates, and that's where he met her. And he fell in love with her when she started talking about uranium and stuff. So that's so he tell us yet that you said that. So Oxford Associates trained her well, I guess. I've had some association with John in the past. We've done a little research together about 10 years ago, and I've had interactions with him from time to time through the Health Physics Society. He won the L. Anderson Award in the Health Physics Society. He's currently the chair-elect of the national organization. And what else? Let's see, remember everything here. Look at my notes here. He graduated undergraduate from Berea College, and he has his master's and Ph.D. from the physics department at the University of Tennessee, and they offered the health physics program. He's a diplomat of the American Academy of Health Physics. He was named a fellow of the Health Physics Society in 2000. And I think that's about it. And if I missed some things, John, you can fill them in. How's that?
That'd be great.
I'll give you Dr. John Frazier.
And thank you. We'll get that name and make sure that you get
Somebody wants a job.
He didn't tell you everything about me. As of 26 hours ago, I became a grandfather for the first time.
All right.
So I think I did. So I just came from there. In fact, I was eating a sandwich. I went by there and I spent most of my lunch at playing with holding the baby, little boy, another John Frazier. And so I told my son, I've got to go. They've got this packed house over there, and then I got over here, it's about half packed. But I'm sure it's quality is what we're looking for. I gave a variation of this talk at the University of Cincinnati about a month ago, and for some students there, and it was like a presentation with cameras and all this thing, and they videoed it to Ohio State and things. It took 20 minutes to get it going, but we're all ready to go here right now, so we're in good shape for this thing. I am the president-elect of the Health Physics Society, and part of my responsibilities are traveling around to student branches and to the various chapters of the society. And since I live in Knoxville, I live out in Farragut, and I thought it would be an opportunity to offer to Lee to give a talk to the students here and faculty, and he said, well, let's do the seminar deal. I think he's always looking for someone to speak at the seminar. That sort of sense that, too. But I knew Pat Dempsey at the time. She worked for us out at Oak Ridge at the laboratory we had out there. I'm probably going to take my coat off since it's warm in here, if you don't mind. And this down here. Is it Gary? Gary explained to me the wonders of this thing here, but you just tap it or tap it twice and you go to your next slide. It's just like my little mouse pad on my computer, and it's pretty impressive type of stuff. I'm a fairly normal person. I did get except for being a physicist. That's abnormal in a lot of ways. But one of the things I got interested in when I was about 19 years of age was radiation detection and measurement. I was a sophomore at Berea College, and even this was in 1967. And so we had a gamma ray spectroscopy system. We had some counting systems. It was one of the early gamma spec systems, 256 channels, which was pretty impressive back that time. Got interested in that in a special class I was taking, and then when I finished at Berea College, I applied for the Atomic Energy Commission Fellowship in Health Physics. I needed graduate support. I couldn't funding, so I applied, and I wanted to do my research at Oak Ridge National Lab. So I thought Tennessee would be a great place to go. At that time, they still had the program in place. The AEC had a program. They had students coming through the physics department then that hosted that program. And before I could start it, I got drafted and sent to Vietnam for a year, but got back from there, and then while I was gone, they closed the program. I thought that was nice. Canceled the whole funding program, but they saved me 1 year. And so I continued in that interest in radiation detection and measurement all the way through, including my research. My research was negative ion resonances in the fluorobenzenes and biphenyl. Now that with 50 cents, we'll get the standard small cup of coffee, whatever. But it was an interesting subject because we looked at low-energy electrons interacting with matter, especially large molecules, and how they're grabbed onto and held into these large molecules and forming negative ion resonances. But over the years, after finishing my Ph.D. and then working for the Bureau of Radiological Health, I worked there on instrument calibration and thermoluminescent dosimeters used in medical applications, measuring the high doses you get from medical procedures. You still get high doses from medical procedures, and there aren't not a whole lot of control for that because they look at the benefit and the risk from that. Continued with that interest there, and then went in 1980, went from Maryland back to Oak Ridge and worked with Oak Ridge Associated Universities, where I think, Dr. Grower, did you not work at Oral for how many years?
Yeah, I don't know if they overlapped or not.
Yeah, I think we did overlap a little. I was there from 80 to 86.
Yeah.
And in that role, I was the coordinator of the health physics training there, so I taught a lot of students, a lot of student groups coming through there, and so I really enjoyed the teaching part of it. But one of the things you really learn when you're teaching, of course, is if you're teaching radiation detection and measurement, is you learn as much or more than the students because you're preparing for those presentations and you're actually doing hands-on, and you get the benefit of the students, especially in those professional training courses, the 2-week or 5-week or even 10-week courses of those students coming from industry and different applications to explain to you that you might be teaching it one way. They say, no, there's another way. Oh really? And so you learn from all those folks. Over the years, I really appreciated that learning experience I had in that teaching role. And then the last several years, starting in '86, I went with IT Corporation Environmental Engineering Group. Worked with IT Corporation for about 7 years, and in the last 8.5 years, I've been with Offshore and Associates. We're a small business located out where I-40 and Pellissippi Parkway cross. We're on the northwest corner up there. We have a total of 23 employees, I guess, and all we do is health physics. The group at our office are primarily the senior types with Ph.D.s and certified health physicists. We have, I guess we have 6 certified health physicists, and we have 5 Ph.D.s in our office there. And one of the things we do is public meetings, interacting with advising clients, corporations, organizations. We work in litigation support. One of the areas we help in. We look at site characterization, radiological measurements, and environmental areas. Look at decontamination, decommissioning activities to make sure that the plans are in place, the procedures in place, and then they're implemented correctly. So we do a wide range of things, and all the way through this, I've been coming across radiological data or radioanalytical data that have some aspect of it that makes me say, I wish I'd really been told this when I was studying this. Because there's certain aspects of the radioanalytical data that I'm going to say almost like nuances that are really informative, important, but we often miss those because it seems like when we go through school, we go through and whether we get a bachelor's, a master's, or a Ph.D. degree, and we come out and we get a laboratory report, something like this, or we might only get, you may not be interested in the full laboratory report for a bunch of samples. You might just take, let's just take the summary of this report, which has the basic data in it. And we look at that data and say, oh, okay, I see, we got lead-210, radium-326, decent. What did lead-210 decay by? Well, anyway, it's all in here, I'm sure. The results are right. So we tend to forget the basics of the radiations, the basics of the interactions, and the basics of the detection. And we shouldn't, because those are the things that you will need to really understand the validity of the data and the applicability of the data. So if we, let's see, get it right here. Summary. I'll give you the end, and if you want to leave, you can go ahead and leave. They don't have to stay for the whole time, do they?
Yeah, if you want any refreshments, I do.
Refreshments, you got to stay. Okay. Somewhere here's where's the button thing? Oh, I just touched it, don't I?
Yeah.
Okay. First thing, I'll try to become a little more orderly, a little more whatever you say here. Learn the details of the analytical procedures and the counting methods and equipment before you try to interpret the data that you get. If you request a particular analysis to be done, make sure you know what is being done. What is the procedure, the methods being followed, what instrumentation they're going to be using when you get back. So that means calling up the laboratory director that you're getting your results from. Do that. And maybe even you'll be the one who's generating the data. Don't follow that procedure just blindly. Make sure you know what you're looking for there. And then second point, don't rely on the summary report until you've reviewed and validated, and I put that in quotes somewhat, validated the entire raw data package. Okay? Because this raw data package, depending upon what level, there are different levels of data reported by the laboratories, the raw data can indicate what may be right and what may be wrong with the data that you have there. And then the third thing is check out the limitations of the radioanalytical methods, and therefore the limitations of the data before you start forming any conclusions about them. It never fails that during an average year, I'll have 2 or 3 calls from individuals in some state or states who have gotten lab results back on their drinking water. And they'll say, well, the state tells me that these are real high concentrations. What do you think? And I'll say, send me the data. They'll send me the basic data. I said, who did the analysis? Can I get the full report? And you look at the full data, and what you find out is that, and we'll talk about this, is that solids contain the radioactivity in H2O. It's not the hydrogen or the oxygen. And so by looking at those data, the raw data, you can determine how much solids are in the water. In fact, you can determine whether that water would even be potable or not in terms of too much solids in it, because there's sort of a cutoff. You know, generally we won't drink a glass of water if you can't see through it. Now, some of you may do that in some of the dorms. I don't know where you live. but generally in Knoxville, if we can't see through the water pretty clearly, we won't be drinking that water. So these are the things that I'd like to get to if we go through this. And what are these radioanalytical data? So that's step 1, basics, 101. Somewhere here it comes in. Basically, these are the results of analysis of radioactive materials. Okay? Very simply stated. We could probably give other definitions, but for the context of this presentation this afternoon, this is where we're going. They usually include the determination of activities in the sample, and they may also include the identities of the radionuclides in the sample. Some of your analytical methods are gross methods that don't tell you what radionuclides are there. It may be a gross alpha or a gross beta. Others would be very specific. It would be the isotopic uranium or isotopic plutonium contained within a sample. And so these are the radioanalytical data we'll be talking about. And how they used, some of the very practical things about their use. There we go, 2 tabs. One is to assess the identities and quantities or concentrations of radionuclides in the samples. Now these samples may be from environmental collection, maybe water, soil, air, some other combination of solids, liquids, and gases, to see what's in those samples. These samples may be from within you. They might be urine or feces or nasal swabs or something like that as part of an internal dosimetry probe. But these are radioanalytical data acquired from that. And they may also be a part of some chemical or biological research procedure. In traveling around during this year as my role as president-elect, I go to a lot of different places, visiting the chapters. I've visited not quite half of them yet, and I'll visit the other half probably next spring. That's most of all those scheduled. You get to see lots of different uses of radioactive materials, and there's still a pretty wide use of radioactive materials as tracers in agricultural research, medical research, and chemical research. And some of you may participate in the use of that. But that's another application of that, and the importance of making sure the data are good, valid, and reliable. My outline today, I want to look at, let's see here, assay of materials, typical radioanalytical data you might have, 3 case studies, 3 examples. I was sharing with these fellows earlier here that I told one of my coworkers this morning, he said, why are you wearing a tie? I said, well, I've got to impress people. No, I said, well, I've really got to give a talk this afternoon at the nuclear engineering department. I don't normally wear a tie. And I said, I wanted to, represent the Health Physics Society by wearing a coat and tie. And he said, well, good. He said, what are you speaking of? I said, well, this is the technical talk. This is not the talk about why you need to join the Health Physics Society. This is the talk about radioanalytical data. And I said, what I wish I'd been told. I said, I've got to be using 3 case studies. And he said, let me guess. So he guessed all 3 of them without any extras. That's pretty good. Because it's 3 case studies that he knows I've been involved with for several years, the types of things that coming and going. And where we have to explain it over and over and over. Fortunately, we get paid to explain it over and over and over to the clients we have. But still, I wish there was a broader understanding of these some of the basic things about radiation detection and measurement. And then the last thing is the summary, but you can guess what the summary is. That's the 3 points I showed you earlier, right? Assay, basic principles, gross counting techniques, alpha spec. Any of you ever done alpha spectroscopy? Good, some, okay. But now, how about gamma spec? Have you done gamma spec? Usually a few more. See, alpha spectroscopy, most people say, well, I didn't really do that, because you got to do a lot of wet chemistry before you get to the point where you can do the alpha spec. You got to actually chemically extract the element that contains those isotopes that you're looking for. And then you would mount those on a very thin substrate base so that you could then do the alpha spectroscopy. So alpha's a little tougher than the other. You got to get that sample prepared. Whereas on gamma spec, put that dirt in there, dry it up first, maybe blend it, put it in a container, and either in a Marinelli or some other arrangement near the detector to do your gamma spec. But either of these, we're looking at a energy spectroscopy, energy measurement of these two types of radiation. Okay, the basic principles of radioassay. I put this up here. It's pretty obvious, but you know, there's always one person. Oh, yeah, that's right. The radiations that are emitted from a sample are detected and measured or counted or whatever measured to infer what's in the sample, what radionuclides are in the sample. That's pretty much what it is. Now, that's the same concept as bioassay, in vivo bioassay. How many people have been in a whole body counter? Okay, there's a few of us in here. Whole body counter is the same principle. You basically put a radiation detector or detectors near the individual, and you measure the radiations, penetrating radiations coming from the individual, and by appropriate calibration, you then infer what activity is in that individual. You may only be looking at, say, the lungs, maybe looking at the gut, maybe looking at the whole body. I had a stress test done, heart stress test the other day, and basically that's what they did, except they did a little bit fancier. I did it at Park West, I guess, hospital, Fort Sanders Park West. I didn't know they were going to shoot me up with like 33 millicuries of technetium-99. I got back to the office and I was glowing, so to speak. All of our instruments were off scale, but they did that so that because we're using environmental instruments, we couldn't. All the instruments were pegged on the least sensitive range, just whatever. But they're trying to see where these radioactive materials will be taken up by the heart muscle itself. They actually load these radioactive materials onto compounds that are taken up by the heart muscle. It's called cardiolites, I think is the compound that's the trade name for that compound was used to me. But they loaded up with technetium-99M, the metastable. That's the 6-hour half-life. And then they image actually where the activity is. They determine the gross activity, but they also use that to give an image of the heart itself, sort of a three-dimensional image to a degree there. Now, the identification is made usually with radiation-specific detectors and energy spectrometers. So if you've got a detector that detects only alpha particles and great rejection of beta and gamma, then that would be the type of detector you use. Then the activity itself, though, you would identify with some type of radiation-specific or an energy spectrometer. And then the activity is done with a standardization procedure. I assume that sometime in your process you've gone through the steps of assaying a sample. Assaying the sample by these steps you're really going through. Looking to radiations coming from it in a particular geometry and location, identifying what those radiations are, and then determining the activity in the sample through some type of a ratio and proportion or some type of, and maybe even an absolute method. I was going through this the other day with a young employee at our office, and I said, if you use coincidence counting methods, you don't have to have a standard source. He said, sure you do. You still got to calibrate your system. I said, no, for if it's coincidence counting of two discernible types of radiation that you can detect separately, you don't have to have a standard. So you can do absolute counting with that. And a lot of folks tend to forget that type of thing. So the basic principles here, I can tap it, right? Let's look at gross counting techniques, the sample preparation. Any of you ever done any air sampling? Collect an air sample? If I wanted to find out what activity is in the room, we would collect an air sample by pulling perhaps taking a grab sample, by just evacuating a container and then going in the room and opening it up and letting the air go into the chamber. Grab sample. But in the case, you might take air and flow it through with a air pump to flow it through a filter and collect onto a filter the particulates in the air, particulate filter sampling, and then assay that filter. Sample preparation may be for a solid, may be some other method of putting it together. It might be a liquid sample there. But in gross counting, you may just be looking for the alpha particles themselves. You need, in that case, an alpha-specific detector. And keeping in mind that for alpha, self-absorption within the sample matrix is critical. It's really critical. You've studied about the range of alpha particles in air and all these things of alpha particles, where they would be in different situations. But the consideration for counting is really critical with respect to that self-absorption. And then for gross beta counting, again, the sample preparation is important, and the self-absorption is important, but not as important as the gross alpha. And then the gross gamma counting is a gross method. Some folks use that, and in the old vernacular, I think it's pretty gross because you can't really determine too much from it. From gross gamma counting. You still see people doing it, but it's not as useful. These are gross techniques where you're actually looking for all of the alpha emitters, for instance, coming from within from the sample and trying to infer the total number of alpha emitters, total activity of alpha emitters present in the sample. This technique of gross alpha and beta counting is often used in tandem. Gross alpha, gross beta together with detectors that inherently discriminate between a count from an alpha particle and a count from a beta particle. And so you can simultaneously do gross alpha and beta counting. That's often done for air samples. It's often done for water samples, where you're trying to determine the total alpha activity present in the sample and the total beta activity in the sample. Both of those are terms, those are units, gross alpha and gross beta, that are related to levels of protection for air samples and for water samples, drinking water, in terms of acceptable levels. The discrimination is often done with a gas flow proportional counter, where that the large pulse, electronic pulse, is due to the alpha particle, and the smaller pulse would be due to the beta particle. Any of you done low background alpha beta counting? Some, got a few folks done that in here too. It's a pretty much of applied thing for air sampling and water analysis. Now the spectroscopy on the alpha particle, the key thing there, as I mentioned already, is that you've got to prepare the sample. You've got to chemically, from an aliquot, you would add a tracer of a known isotope of the same element you're working with. And what happened? I did? How did I take it? That was slick. Must have moved my hand away. It's magic. I know these things are magic. You add this tracer, and then you chemically extract the material. For instance, let's suppose you wanted to do alpha particle spectroscopy of uranium. Now, let's suppose we're looking at uranium in water, okay? Isotopic uranium in water. And I know that the isotopes of uranium in water naturally would be uranium-238, uranium-235, and uranium-234. So if I wanted to use a tracer that's radioactive, a radio tracer, to add to this of a known amount, then I could put that into that aliquot of water, a known amount of this tracer in there, and then I could, when I do my chemical separation and do the extraction and ultimately the alpha spectroscopy of it, I would have a known activity that I could refer to determine the overall process yield, or the overall efficiency of the system, if you will. And so for uranium, typically uranium-232 is used, not naturally occurring, but a radionuclide that you can purchase from NIST and use that as a tracer there. And that gives you the discernible isotope of the same element that you're looking for there that will show up in your spectrum. And then the counting the sample, after you've mounted this material, brought down into a very thin sub-mount. Some of you may have actually prepared alpha samples of alpha emitters for counting. You're talking about a very thin planchette, typically anywhere from an inch to an inch and 7/8, or maybe less than 2 inches diameter planchette, metal base on which a sample is prepared. And then that sample is put beneath the alpha particle spectrometer. I say beneath, very close to it typically, that you like to have. I'm getting ready to mark on the board. Just can't hardly wait for that. And inside of a vacuum chamber, and then you would use your energy spectrometer, your pulse height analysis, multi-channel analyzer type of things. Now, if I pick this thing up here, this would indicate that I have a blue one in my hand. I need not even use this. He explained this already. And so if I were to look at my counting here, I would say, that's blue, just maybe another color below there. That would be my base there on this thing, and then onto it I would put my material here. My sample would be brought down probably from an ion exchange column down onto the base. And then I would put this whole system then beneath the, I put it beneath the detector, like this, spectrometer. And I won't get into that. I'm sure that the folks who cover detection here will go through silicon surface barrier detectors and other types of diode detectors for alpha spectroscopy. But in any event, this detector has essentially a dead layer. Wrong color here. I put this one back. There we go. Simplicity is my middle name. Okay. So what we have here, I didn't draw it very good. We have basically a dead layer here, through which the alpha particle must pass before it gets to the detector proper in this region here. And in passing through that dead layer, the alpha particle is going to lose some energy. So it's now lost a little bit of its energy in a region, this window here, that was not the detector proper. So if I'm determining the energy that is depositing in that detector, it's going to be a little less than it would be if it went in there without that window. Now this sample that I had down here, on this base here, looking at the alpha particle coming through it, some of the alpha particles coming out of the sample may have to go through quite a bit of material there. Some of the alpha emitters may be at the top of the sample. So if we have an alpha emitted from the bottom here, it has to go through a little more material before it comes out, so it's lost a little more of energy. And then similarly, when the alphas come off, they may go straight through the window, the entrance window, or they may go through it obliquely, such that they have a much longer distance there. In either case, what we see is that for alpha particle spectroscopy, instead of having the number of alphas that you're counting, if I go slow enough, it's pretty good, by the energy of the alpha particles, instead of having a nice line here, say for something like plutonium-239, typically you have about 73% of this energy and about 27% of this energy. Instead of having this, you actually have a piece that has this, like this. The alpha particles peaks are not symmetrical. They have a low energy tail. And why is that? The alpha particle has lost energy coming out of the sample. Okay? Maybe you have different the thickness of material to come out. It's lost energy, perhaps even if your vacuum chamber here in going a greater distance, you have a little bit more energy lost if you don't have a real good vacuum. And then when it goes through the entrance window, or the detector window there, I put that in quotes sort of, it's lost, some of it may have lost more energy. So you always have the low energy tail on the alpha peaks. Okay? Now you can improve that by moving this, making an extremely thin sample and moving the sample further away. Your geometry is better down this way, but what does it mean about how long you have to count it? To get the same number of counts you're looking for, to get the same counts in your peak, you've got to count it longer. So if you're running a laboratory, you want that sample up close because of some sort of a compromise there. And so I get to this point because one of the case studies we're going to talk about is how this can really interfere with your process there. Can I just tap this and it goes away? Oh. Okay. So I showed you that theoretical spectrum and then the actual spectrum you have from the alpha particles there. Very fundamental concept. Now the gamma ray spectroscopy, which I hope all of you will do before you leave here, that you'll have a good gamma spec system, don't you? Okay. Gamma spec, certainly you prepare the sample, put it in some type of container. You typically will separate out the solids, liquids, and gases there. You would select some aliquot from that, and then you containerize it. You may even seal it up to let it come into secular equilibrium. Because oftentimes with gamma spectroscopy, one of the things you can do is to count a short-lived daughter and assay it in lieu of the parent. Here's a good example. How does cesium-137 decay? Does it emit gamma rays? There's usually some people that nod and agree. Cesium-137 is a pure beta emitter. It doesn't emit gamma rays. Cesium-137 doesn't emit gamma rays. But we assay cesium-137 by assaying its short-lived daughter, barium-137M. Okay? But its half-life is so short compared to the cesium-137's 30-year half-life that it's already in equilibrium, equal activities, concentrations of that material, the daughter and the parent, secular equilibrium. So it's there. And so that's a consideration you may make for gamma spectrometry. But then after you prepare the sample, then the sample is counted by following an energy calibration of the system and an efficiency calibration system. Those are different things. Now, one energy calibration you do to identify the gamma rays emitted. Efficiency calibration is used to allow you to determine the activity present. Okay? And then the counting geometry should be the same for these two, for the efficiency calibration at least. And then your spectrometer. Y'all use a high-purity germanium detector here?
Yeah, three of them.
Three of those, and what multi-channel analyzers? Are they all PC-based systems now, or?
We have two membrane-based systems.
Okay, good. And then the data themselves. Typically, you're talking about the result will be the analyte. Whether you're generating the report or someone else is generating the report for you and you're reviewing it, you have the analyte. You have the result. I'm using picocuries. I could have used kilobecquerels or becquerel, whatever, but depending on where you're talking, it's different things. The uncertainty, oftentimes, is given in 2 standard deviations of the counting error, and you all probably go through that somewhere in your counting classes here of the proper way to present the uncertainty, and that way is probably, you can get a lot of good arguments on how you present that uncertainty, and whether or not you include all the uncertainties, not just the counting uncertainty. But when you get a report back from the laboratory, or if you're generating your own report, make sure that you understand how the uncertainty is presented, what it represents. And then the MDA or MDC, minimum detectable concentration. In other words, how good is my system, or how good is this analysis here? What would be my minimum detectable concentration I can measure with this system? And here's an example of a report that we might find from something here. Is that labelable? I'm sure you folks in the back can't see it, but that's why you went in the back, wasn't it? You find that this is a typical type of a printout here where you have a bunch of results. In this case, this is a real case. You may have read about the 45 minute. Well, I won't get into that because we're on TV. I don't. Anyway, this is out in Denver, and these were isotopic uranium results. Uranium-234, uranium-235, and uranium-238 for these samples. You would find that there would be a known sample that's put through the system, and a spike that's given a known amount of the of that U-232 in this case, the blank, and then you've got a duplicate in the lab, and then you've got another case. So I need to go back. How do I go back? Sorry. Drag this up?
Yeah. Not the arrow, but the...
There it is. Sorry. Anyway, even as we go along, can you back page me? Thank you. Good man. Okay, now, the example of a report like this where we have the samples here for uranium-234, 235, and 238, isotopic uranium of samples. They typically would operate in a batch mode so that the quality assurance data for this batch could apply to all the steel samples in there that are used for that. This is following a standard analytical procedure. In going through these methods, we could use a gross counting method or a spectroscopy method, either of those, to come up with results. There's 3 cases I wanted to look at, 3 case studies, and my time is about where I thought we would be at least. One of the case studies is gross alpha and gross beta analysis of water samples. Okay? And this is one of those examples where you hear a lot about. And when you get out into the working arena, whether you're working as a nuclear engineer, a health physicist, or whatever you're doing, and someone comes to you with gross alpha, gross beta water analyses, the first thing you should think about is solids. The solids in the water. Because as I mentioned before, the hydrogen, that's just regular hydrogen, and oxygen, the H2O, has no radioactivity associated with it. So when you're taking a gross alpha and gross beta analysis of a water sample, you're really analyzing the alpha emitters and the beta emitters that are in the solids in that water sample. And all water has some solids in it. The solids may be dissolved or they may be suspended. And so if they were, I can mark on this without even going along here. If they're dissolved solids, we can have the total dissolved solids in the sample. If they're suspended solids, you guessed it. And these are the terms that are often used for the solids in the sample. Okay? Many analyses of water samples don't give you that information. But a gross alpha, gross beta analysis, the procedure that's followed for that, necessarily includes the information of the solids in the sample. Okay? So that information is contained in that report that you would get in the raw data, not the final report, but the raw data for the analysis. And that's important if you're trying to relate what these results mean. Okay, let's put this back with the light goes off. And this is the example I'm talking about. We have some groundwater samples that came out of the ground. Okay? May not be anyone's potable water supply, but they're out of the ground. Maybe out of a well, maybe out of a hole in the ground. So I just stuck down out there. I mean, it's with a shovel or something. But these the gross alpha and gross beta concentrations are higher than the maximum contaminant levels, MCLs, as specified by the. You all get into regulations here, too? Not much, okay. Well, Title 40 is EPA, Code of Federal Regulations. 141 is the part that pertains to the Safe Drinking Water Act. Okay? So that you would take a water sample coming out of the ground, they take an aliquot of that sample, and they analyze it, and they say, wow, this has got a lot of gross alpha and gross beta. Obviously, we got a lot of contamination here from someone's activity, okay? But the water is not expected to have any man-made radionuclides in it, okay? So let's look, see what's next on this thing. Here's an example. Unfortunately, you can't read this one too well. I can't zoom on this sucker, can I, with the way it's structured now, can I? Okay. But I could have done this, I thought, before I came and zoomed. That's right, my fault. So, here's an example. Here you can't see it back there, but this sample here is, let's see. This is gross alpha. All these are gross alpha. The known, or the spike we had up here was 274 picocuries per liter, plus or minus 7.4 with a MDA, or actually an MDC, should be, but they call it MDA at the lab, 0.6 picocuries per liter. That's pretty good sensitivity. They ran a blank through. It's distilled water. And it came out the negative at result. So it was slightly lower count than you got from their background count of the system. And the uncertainty is 0.2, and then the MDC or MDA is 0.8 picocuries per liter. So it shows that their sensitivity is about 0.8 picocuries per liter. Pretty rough. I mean, if they want to quantify it, we could get real technical about that. But then here comes along a sample from this property. In fact, I testified about this last week in Mississippi, actually all day last Tuesday. Somewhat about this. This particular sample here has 667 picocuries per liter gross alpha, with an error of 396 and an MDA or an MDC of 374. Right? So is that a real number? Well, I looked at this one and I said, this is strange. What is this thing? This is water out of the ground, but it's called produced water. This is water that comes out from an oil-bearing formation. This water here has about, for every liter, it has about 250 grams of solids in a liter. So if you dry that thing down, well, you can see through it, but most of these solids are salts. Okay? There's the salt water. That's the reason. And so if you were to analyze this thing, you say, gosh, look at this. I went back and looked at the raw data and say, well, how in the world could you come up with if your detection, your MDA is supposed to be this good, or MDC is supposed to be 0.8 picocuries per liter, how could it possibly be 374 picocuries per liter? And that's the trick. The procedure says you can only use on your planchette, when you dry down this alkaline water, you dry it down onto the little metal planchette. When you dry it down, you can only have 100 milligrams of material on the planchette. So the lab said, what size aliquot can I have that when I dry it down, I'll have 100 milligrams left? Well, they determined that initially by saying, let's look at how much solid's in the water initially. Well, they determined that the smallest amount they would have to have less than 1 milliliter of water. Normally, they would use perhaps 100 milliliters or 200 milliliters, 400 milliliters to dry that. But because there's so much solid, they only use 1 milliliter. Now, if I had taken the time to prepare my lecture to put together the formula, you would have seen that the detection limit, the minimum detectable concentration, is inversely proportional to the volume of the sample. So if you have a real small volume, it shoots up your MDC. Okay? And this reflects here. If I look at this, I can say immediately, high MDA or MDC meant there was a lot of solids in the sample because they had to take such a small aliquot to meet the procedural requirements. Okay? And so when you see gross alpha and gross beta results with a real high MDC, the thing that stands out is, I don't even have to look through raw data now. I know that there's a lot of solids in there because they had to have a small aliquot to use. And that's a very practical thing you can use in interpreting these types of data. This is one of the simpler things you can do. Now, some of these samples, if you look at those, you'll also find that this sample here was from a well, had 0.7 picocuries per liter gross alpha and 0.6 picocuries per liter gross alpha in this one. But the 0.7 is less than the MDC, and hence most folks would say, well, that's not even quantifiable level there. So that these levels are probably not much solids in it. You can look at the results to see that. But it's a very practical thing about gross alpha and gross beta for water samples. And I wish I'd been told that when I was going through learning how to dry down the aliquot and count the thing. I knew that you'd only limited to the certain mass you had on there. But when I get results back, I look at the results, and I only usually go over here and just look at this part right here. Maybe include the uncertainty. I'd look at the result and the uncertainty, and that's what we got. Okay? Next case. Let's see if we can go down. Alpha spectrometry of uranium isotopes. This brings Dr. Miller in here. Dr. Miller, have you ever had any soil samples that were analyzed for alpha spectroscopy for uranium?
About 1,000 of them.
About 1,000 of them. When did we do that, Dr. Miller?
That's 1986 or so.
Yeah, about 1987, and we appreciate that help very much, sir. Those samples were collected around the Fernald plant, the Department of Energy plant, in almost on the Indiana border. It's west of Cincinnati. That's the former Department of Energy Feed Materials Production Center. That's where they used to use uranium. They would take uranium and low enriched uranium, but still slightly enriched, about 1% enriched, and they would make from that uranium metal that was then used as feed material for plutonium production in the production reactors. You bombard the uranium rods with thermal neutrons over time, and you are transmuting the uranium into plutonium, and then you take out the uranium rods and you chemically separate out the plutonium from it. Okay, that's not classified or anything else. That's just the way you produce plutonium. But at this facility, they work with a lot of uranium, and so there was claims of contaminated soil off property. So these 1,000 samples or 968 samples or whatever we had there came primarily from the property boundary out to 5 miles. We collected those samples in 1986. Out to a certain distance. And one of the things we started finding out is get alpha spectroscopy on these things. And the concentrations of the uranium-235 and the U-238 determined by the alpha spectroscopy of the soil samples indicated that these samples had enriched uranium in them. Some of these samples were collected 6 or 7 feet deep in the ground, away from the property so far, and up gradient, so there's no way that any surface water or groundwater could ever run there. I mean, these were truly unaffected samples, many of them were. Now, some of them off one side, you could measure a little bit of that. But people will take alpha spectroscopy data for uranium-238, 235, 234, and they will then say, well, I can determine the enrichment. Let's look at the activity of the 235 and the activity of the 238 and take into account the specific activity, convert activity to mass, of the two. I could calculate the mass enrichment. And we were coming out with anything from from 2% enriched up to 5% enriched uranium. Okay? Now, I've had that same problem happen again in the near Pittsburgh at the Apollo facility. There also they work with the enriched uranium. And in that particular matter, that was a lawsuit also. Folks were using those data to show that off-site uranium, even out to miles, was from this plant's operation. Now, what's the problem with this? Did I tap it twice? Okay. We look at the uranium-238. You probably learned this a long time ago. Many years ago, folks would say, the longer they live the radionuclide, the lower the energy of the alpha particles. Is that called the Geiger-Nuttall rule? Remember that somewhere along the way? There's a rule. You can actually plot them, you see. So uranium-238 is the longest lived of the isotopes we have here, and therefore its alpha energies are lower. You can't see those, but it's about 4.2 MeV. Uranium-235 is not as long-lived as 238, so its alpha energies are higher. It goes from, well, primarily we're talking about stuff here in the range of probably 4.4 MeV. So we go from 4.2 to 4.4. We can separate those with alpha spectroscopy. But U-235 has lots of different peaks there. And then we look at 234, it's even shorter lived than these two, so it has even higher energy alphas, and so it goes up to about 4.8, 4.7, or 4.8 MeV. So that's also discernible with good spectroscopy. And then the tracer, remember the tracer we added for the alpha spectroscopy, we put that in, that's the U-232, that's added, and it's short-lived compared to these others, and it has an energy well up there of 5.3 MeV. So if I look at the idealized spectrum, I would see something like this. Ideally, I would have, let's see, pick this up. Ideally, I would have my spectrum be something like this. That would be U-238. 235 is all these little guys down here. Actually, 235. Well, this is handy when you're doing it this way. And the 234 is up here. Ideally, would be something like this. And actually, I think it's here too. So, and this is the 234. And then the tracer that was added is here, like that. This in this region. Okay. Now that's typical what you would find if you had a perfect detector and a perfect sample. Okay. But remember, what you don't have, or what you do have with a real system. Each of these guys, because of sample preparation and sample counting and things, will have a tail. So that this guy here, this 238, will be something like this. And the 235 will be something like this. And the 234 will be something like this. Look what happens with all this 234 that's in there, because when you're doing the quantitative counting, you're looking at a region of interest. You might set your region of interest something like this. That's the 238. And the 235, you probably set your region of interest something like this. Like this. So you're counting all the pulses that fall in that region. And then the 234, you probably set your region something like this. And then the 232, which also would have that thing, you put it up here like this. It doesn't take very many counts for the 234 to fall in there to increase your 235 counts over and over again. Now, you can say, well, there's no way I can use alpha spectroscopy to determine enrichment of uranium in a sample. Not totally lost. Not totally lost. Certainly, you would not want to use 235-238 ratio because of the 234 interference. It's going to come down in that peak. Okay? Come down in the 235 peak. But what you can do, you can look at the 234 ratio. And if I could go back to the 234 ratio, 234 would be these counts here, and the 238 these counts here. For normal soil, Dr. Dodds, I'm glad you made it. Everything's okay then. I just told them I'm a grandpa. A little over a day ago. I've got pictures, but they're 8 by 10. Digital cameras now, you can do anything with them. So with the 235-238 ratio, you've got a problem with that bleed over. But with 234-238 in soil, the 234 and 238 in soil are essentially the same concentration naturally in soil, because the soil and the rock from which the soil is derived and those things have been there for many, 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 many years. Okay, you can't say the same thing, or he said, I said you can't say the same thing. And he says you can't say the same thing about 234-238 ratio in water. 234-238 ratio in water is not 1-to-1 necessarily, especially old water, like underground caverns been there for hundreds of thousands of years or whatever. Because old water formations, sometimes you can have 234 that has real high levels compared to 238. Sometimes you can have lower levels. But for soil, you can use the 234-238 ratio, and by looking at the 234-238 ratio in the soil samples, you can infer the enrichment of the 235 mass that's there. Now, the reason that this is possible is that the uranium enrichment we have that would be in the environment, at least, if there is any man-made enriched uranium in the environment, how would it have been enriched? Generally, you could say it was enriched by what process? Gaseous diffusion. And these data and this plot here is for uranium that has been enriched by gaseous diffusion. You can't use that same logic for atomic vapor, laser isotope separation, or some of the other enrichment techniques. Okay? But for gaseous diffusion uranium, which would be the type you could find in the environment, this would be that relationship. So if I have a 234-238 ratio, that's 2, then I could say, yeah, we've got 1.6% enriched uranium there in that sample. And in fact, I use this on that Apollo case, Apollo, Pennsylvania case, to point out that, yes, unfortunately, I guess that the defense didn't really care too much for it, because I was saying, you can't use the 235-238 ratios. And then, to be honest, though, you have to say, but you can use the 234-238 ratios. And there we showed that there was off-site contamination after about 300 meters. Instead of 3 miles, there was some off-site contamination after about 300 meters. Okay? And so this is an application of that. But going all the way back to here, remember, it's the tail of the 234 that comes into the 235 peak that causes the problem. You can't get rid of the tail totally. Okay? And then the third case, and I'm glad you made it to the third case, because this is about radium-226 in soil samples. Okay? Most of the folks who have done spectroscopy in here have done gamma spec. And one of the easier things to do is to do gamma spectroscopy of soil. Typically, you'll dry the sample, blend it way out to an aliquot that you want, typically maybe 800 grams, maybe a whole kilogram. And then you would put that in a Marinelli beaker and seal it up, or put it in a beaker, and count it around or near that detector that you're using, high-resolution spectrometer. But it's not uncommon to have radium-226 concentrations in a soil sample, reported by the lab, that have higher concentrations than the short-lived daughters, lead-214 and bismuth-214. Even after you seal it up and leave it sealed up for secular equilibrium to be achieved. Okay? Even after the sample has been sealed up for a long time, 28 days, 22 days, or whatever. And so the process for radium analysis, you could use it directly from here, using a particular peak, which we'll look at. Did I touch that? I didn't mean to. Must be buddy. Or I could use its short-lived daughters, lead-214 and bismuth-214. Now, the way I'm going to allow to be used those, to be allowed to use those, I'd have to seal up the sample, because if I don't seal it up, what's going to escape? Radon might escape. And then by sealing a sample up, I will have the radon daughters, including the lead-214, bismuth-214, which have great gamma energies and good intensities that you can detect and measure. So assay the samples here. But if I look at this radium, the reason that radium is important, is that for many sites where you have decontamination decommissioning, radium is one of the radionuclides that has a very low cleanup level. Very few picocuries per gram. Actually, 5 is the recommended activity cleanup level. 5 picocuries per gram, average over 100 square meters, and that's above background. But background of radium in soil is anywhere from 0.5 to 5, typically in soil. You can have a wide range of background. And if you're cleaning up down to a low level there, then the analytical method you use to determine whether the radium concentration is 2 or 6 makes a big difference. Very practical thing you would encounter if you were working in a decontamination decommissioning environment. And so if I look at this, I see that the radium-226 emits a gamma ray, 186.2 keV, but it's only 3.3% of the decays. This is the intensity. Okay? About 3.3%. Uranium-235, which is also present in all soil, because uranium is a primordial radionuclide, uranium-235 is, its energy is just slightly different, and in fact, even with your great systems here, these two lines will fall on the same peak. So whenever you assay radium-226, this is directly, then by gamma spec, you would use this peak, but it has the interference of the 235 peak, okay? And so it's going to give you a positive bias if you use that, because of the presence of 235. In fact, 1 picocurie of U-235 will give you about a 16 picocurie per gram bias up here. Now, obviously, you don't have naturally occurring 235 at this level, but you do have it where that you could get somewhere between 1 and 3 picocuries per gram bias. And that makes a big difference when you're assaying the sample. And so, looking at the results, this is an example I talked about, requesting that the sample be sealed and assayed for the short-lived daughters after sacred equilibrium takes away the problem with this interference here. 3 cases, gross alpha, gross beta of water, lots of solids can give you real problems. Or most any solids will give you problems from the naturally occurring radio alpha and beta emitters in solid. Alpha spectroscopy of uranium isotopes, interference of any alpha spectroscopy, the low energy tail from the higher energy alphas coming down into your region of interest you're looking for. And then the conflicts of radium-226 interference by uranium-235. These are 3 things that I've learned as I have moved through this process of reviewing radioanalytical decay data, But what it helped me to know is that I needed to know the procedures and the counting methods and equipment before I try to figure out what's going on or try to use these results. And then I always look, if I can't get the full data report, my opinion of the data is it's suspect, or I haven't completed a validation. Now, there is no, as far as I know, there is no formal data validation procedure or protocol for radiological data, analytical data. There are some protocols that individuals have developed and used, but I know of no standard protocol. Okay? There are various ones that are out there. Because these validation protocols, they exist for chemical data validation, but not for rad data validation. You need to review the supporting data packages as it relates to the full quality control package, if you will, and look at the supporting data, and check out the limitations of the data. See what those limitations would be of the methods and therefore the data before you draw any conclusions from that. And all of this goes back, to me at least, to this final thing as it relates to radioanalytical data. The basic concepts that you learned in terms of radiation types and energies, how those radiations interact, and how they detect, and then how they're detected. Those concepts are the very things that help you to explain and understand what the radioanalytical data mean. You go through that, learning the basic stuff, and don't leave it behind when you walk away from this place. And people will look at you and say, wow, how'd you know that? And you say, it's very fundamental, basic stuff. I think these are good principles that you can hang on to when you're interpreting radioanalytical data. Thank you for your time.
Okay, question time for Dr. Frazier. Anything you ever wanted to know about radioanalytical data but were afraid to ask? Now's your chance. Questions? Thank you, and we have refreshments downstairs, and let's go have refreshments. Thank you again, John.
Sure, enjoyed it. I should hand these out as they walk by, though.
Oh, yeah. Hang on. No refreshments unless you